नमस्कार बच्चों, मेरा नाम धन्या and we are learning chapter 4 of grade 11 chemistry, which is chemical bonding and molecular structure. In our last video, we learned about the Lewis dot structure and how it could explain the structure. It could tell about the Lewis structure. The Lewis theory could tell about the lone pairs, bond pairs, etc., and the type of bond and the number of bonds, whether it's a double bond, triple bond, etc. But there was some limitations for Lewis theory because it could only explain the structure. It could not explain the geometry or the shape of the molecule. Lewis theory could explain the chemical bonding, but it failed because it could not explain the geometry or the shape. Okay, so the new theory came up, which is called as valence bond theory. Okay, so in this valence bond theory, the concept of sigma and pi bond came into play. Okay, so the next theory that we are going to learn today is valence bond theory or VBT. Okay, so the concept of sigma and pi bonds. Okay, so sigma means it is single bonds. Okay, and pi bond means multiple bonds. Okay, double and triple bonds. Okay, now we know that the electrons are in different orbitals, right? It can be in S, it can be in P, D, or F. Now, valence bond theory explains how the atom come closer and the orbitals, they overlap. So overlapping is between the orbitals. So valence bond theory, VBT, tells about what? Overlapping of atomic orbitals. So in valence bond theory, according to valence bond theory, the overlapping of atomic orbitals takes place. And what is present in these atomic orbitals? Electrons are present. Now, there are some postulates or rules in valence bond theory. According to this, the first rule is that a covalent bond is formed. A covalent bond is formed. How? By the overlapping of atomic orbitals. So when the overlapping of atomic orbitals takes place, then a covalent bond is formed. And this was proposed by Pauling and Slater. Okay, so they were the scientists who suggested this theory. Okay, the second point is that, according to valence bond theory, these are a set of rules, okay, about the valence bond theory, that covalent bond is formed how? By the overlapping of atomic orbitals. And who suggested it? Two scientists, Pauling and Slater. Okay. Now, when these atomic orbitals overlap, there is yet another rule. Only half-filled orbitals. So only the orbitals that are half-filled can overlap, and that too the electrons must have opposite spin. You know that orbitals have electrons, right? So the electrons with opposite spin can only overlap. So only half-filled orbitals with opposite spin electron can overlap. Opposite spin electron can overlap. Okay, so we have 1s, so I'm just giving an example. Okay, if they're overlapping, see both the orbitals are half filled and also the electrons with opposite spin. So only these orbitals can overlap. Okay, now when they overlap, The overlapping must be less than 50%. Okay, so overlapping, the extent of overlapping must be, or overlapping must be less than 50%. What if it is more than 50%? If it is more, what happens is that the nucleus comes closer to each other and there can be repulsion. Okay, now there is extent of overlapping. Okay, so if the extent of overlapping is more, then what about the strength of the bond? Strength of the bond is more. Okay, so more extent of overlapping, more stronger the bond. Okay, so if a bond is very, very strong, suppose if the bond strength is more, it is directly proportional to bond energy. Suppose if a bond is very, very strong, then that means more amount of energy is required to break that bond. So bond energy is more, but the bond length, the distance between the bond is very, very less. So the bond length is lesser. So it is inversely proportional to bond length. So more stronger the bond, it will require more energy to break apart the bond. More stronger the bond length is very, very small. Okay. Now the fifth postulate or the fifth rule is that there are two types of overlapping. So overlapping is of two types: axial overlapping or head-on overlapping. Axial or head-on overlapping. Overlap. The second type is parallel, or we will be learning about these overlapping, okay? Parallel or sidewise or lateral overlap. Or lateral overlap. Okay? Head-on overlap or axial overlap gives rise to sigma bonding. Parallel or sidewise overlap or lateral overlap gives rise to pi bonding. Okay. Now the next rule is that the overlapping orbitals must have the same sign. So overlapping orbitals must have the same sign. For example, p orbitals. Okay, so this is one p orbital overlapping with another p orbital. Okay, so if they are overlapping, the two p orbitals must have the same sign. Those that have the same sign will overlap. Okay, for example, this is px and px. Okay, or if I have py and py, if both the minus sign, these can overlap. Okay, both the minus sign. So those orbitals that have the same sign will overlap. If they are of the different sign, they will not overlap. Okay, for example, if I have one with a positive sign, one with a negative sign, this will not overlap. No overlapping will take place here. Okay, similarly, one more condition is that here, these two orbitals, they have the same orientations, px, px, py, py. The orientation is same. so they can overlap. But in case the orientation is something like this, suppose this is py and suppose this is px. Okay. Here, because the orientation is not proper for overlapping, therefore the overlapping will not take place. So for orbitals to overlap, they must have the same sign. Okay, or overlapping orbitals must have the same sign. At the same time, the orientation must be proper. Orientation must be proper. Proper orientation should be there. Okay, so these are the set of rules. Okay, now let's talk about the two types of overlapping. Okay, so let's talk about the two types of overlapping before we practice some molecules. So, two types of overlapping. So, types of overlapping. First one is axial or head-on overlapping. That results in the formation of sigma bond. Sigma bond means single bond. For example, the s orbital. S orbital, you know, it is spherically symmetrical. Okay, so this is one s orbital. Okay, this is another s orbital. They can overlap head-on. They can overlap head-on to form SS sigma bond. So this is head-on overlapping. Okay, so this is head-on overlapping. It's not sidewise. It results in the formation of single sigma bond. Okay. Now, here again, there can be head-on overlapping between s and p orbitals also. For example, if I have, so sigma bond means single bond, single bond. Okay. Now, as I said, there can be overlapping between sp bond or sp orbitals also. Okay. So before we move on to that, let's take an example of SS sigma bond. For example, first one, hydrogen, H2. So there are two atoms of hydrogen, each having configuration of 1s1, right? So here, one electron is there. In the next hydrogen also, one electron is there in the 1s orbital, but I'm representing with a opposite spin. Okay, so both of them overlap 1s. This is 1s for the next hydrogen. They result in head-on overlap to give you hydrogen-hydrogen sigma bond. And as you can see, it's a single bond. Hydrogen-hydrogen sigma bond. Okay. Now here, again, I told there can be sigma bond between S and P also. SP sigma bond. So SP sigma bond. Okay. So in this, the unpaired electron in the s orbital. Okay, so we must look at the sign also. This is the s orbital, overlaps with the p orbital of p orbital with opposite spin to give you sp sigma bond. So this is sp sigma bond, single bond. So let's explain with an example. For example, if I have HF molecule, HF, okay? So this is the Lewis dot structure. So this is hydrogen. So hydrogen is 1s1. Fluorine is 9. So 1s2, 2s2, 2p5. Okay. So hydrogen is, I'm drawing the unpaired electron or the electron in the 1s orbital. For fluorine, this is 1s2. This is 2s2. This is 2p orbital. So 1, 2, 3, 4, 5. Okay, so I just drew the electron in opposite spin for 2pz. Let's take it as 2pz. We can make any of the 2pz, 2px or 2py or 2pz, any of them unpaired, because all the three 2p orbitals have the same energy. Okay, so the overlap is between 1s and 2p. Okay, so you can take 2px, 2py, or 2pz. Okay, so I have hydrogen here, the s orbital of hydrogen. The s orbital of hydrogen overlap with the 2pz orbital of fluorine. So this is fluorine. Electrons with opposite spin. This is 1s, 2pz, sigma bond, axial overlap. Okay, so it can be 2px, 2py, or 2pz. Okay, any of them. Similarly, if we take for or if we compare, this is hydrogen fluoride. That is in hydrogen fluoride, the overlapping is between 1s and 2p. Similarly, HCl, okay, the overlapping is between 1s and 3p. It can be 3px, 3py, or 3pz. Next one is HBr. The overlapping is between 1s and 4p. Hydrogen iodide, overlapping is between 1s and 5p. Okay. Now, from here, if a question is asked, which bond is, so if a question is asked, so I'm just removing this. So if a question is asked, which bond is stronger, or arrange it in increasing order or decreasing order of the bond strength. Okay, so you must remember here, if the N value is less, that means it is close to the nucleus. That means the nucleus will hold that orbital or the electrons more closely. So that particular bond is more stronger. So if you compare 2p, 3p, 4p, and 5p, here 2p is closer to the nucleus because 1s is common in all of them. 2p is closer to the nucleus compared to others. So the bond strength will be hydrogen fluoride bond is more stronger than hydrogen chloride, which is more stronger than HBr, which is more stronger than hydrogen iodide. Because 1s and 2p, they are closer to nucleus. If they are closer, the nucleus will be held more strongly. And who is furthest? 5p is furthest. Okay. So whichever has smallest shell number, that will be closer to nucleus, and that particular bond strength will be more. Now, bond strength depends upon the N value. Right? If the N value is less, bond strength will be more. If bond strength is more, what about the bond length? Bond length will be lesser. Bond length will be lesser. So, it is inversely proportional to bond length. So, if the same thing is asked, HF, HCl, HBr, HI, if you are asked to arrange them according to bond length, it will be the opposite. Because this is stronger bond, it has less bond length than HCl. HCl has a lesser bond length than hydrogen bromide, which has lesser bond length than hydrogen iodide, because bond strength is inversely proportional to bond length. Okay, so remember just remember the bond strength, bond length is the inverse proportionality. Okay, so these type of questions are very important. Okay, so whichever molecule has lesser N value, bond strength for that molecule will be, or the bond strength will be higher for that molecule. If bond strength is higher, the bond length is lesser, inverse proportionality. Okay. Now, coming next to PP head-on overlap. Okay, so suppose I'm taking PZ. Okay, so this is minus and this is plus. Okay, sign is very important. So orbitals with the same sign, they overlap. Okay, so this is another PZ. Orientation is also important, PZ. This is plus and minus. They overlap head-on to give you PZ, PZ or PP sigma bond. For example, if I have electron with one kind of spin, this is another p orbital with another spin, opposite spin, they will overlap to give you PP sigma bond. Okay, so this I'm talking about the head-on overlap. Okay, this is the head-on overlap, head-to-head overlap. For example, here now itself I would like to just tell that suppose if their orientation is like this, sidewise. This is sidewise. They will not give sigma bond. No sigma bond is formed here. No sigma bond here. No sigma bond here. Because here the orientation is what kind of orientation? Sidewise. It's not head-to-head like this. This is sidewise overlap. Okay, so just wanted to inform you this before I move on. So this is the head-on overlap. Okay, head-to-head. Okay, for example, if I have BF3, okay, so boron fluoride, boron is 1s2, 2s2, 2p1. Fluorine, there are 3 fluorine, so I'm just drawing for now 1s2, 2s2, 2p5. So here, one S2, 2s2, 2p1. This is 2p. This is 1s, this is 2s. Here in fluorine, I have 1s2, 2s2. So 1, 2, 3, 4, 5. So the overlap is between 2p of boron with 2p of fluorine. Okay, so here the orientation of electron is very important. The orientation must be opposite. So orientation, here it is in one way, in 2p it is of fluorine, it is in opposite way. Okay, so make sure that this is shown. Okay, now over here there is one bromine and 3 fluorine, it is BF3. Now we have to share electrons between boron. This is the Lewis structure between boron and all the 3 fluorine. All the 3 fluorine. So this must happen. But boron has only one unpaired electrons over here in 2p. Okay. So what happens is that we do the excitation of electrons. What happens? Excitation of electron takes place. Excitation of electron takes place so that the electrons is available in all the p orbitals for boron. Because right now we have only one unpaired electrons in 2p orbital of boron, as you can see. With this, we can form only one bond. But we need 2 more bonds to be formed. For that, we need electrons in 2py and 2pz orbitals also. Otherwise, bond formation will not take place. So what should happen? Excitation of electron takes place. In which atom? Boron atom. So when excitation takes place, what happens is that the electrons will move from, I'll redraw this once again, 1s, 2s, 2p. 1s, 2s, and 2p. This is for boron. Okay. So when excitation happens, the electrons from 2s move to 2p, one of the electrons. And we get a picture like this. 1s, 2s, one electron shifts to 2p. Okay. 1, 1. This is 2s, this is 2p. Still, even if there is no electron in 2pz, 2pz is empty, but still, do we have there is no electron in 2pz, but do we have 3 unpaired electrons? We got 3 unpaired electrons. So, in order to get the 3 unpaired electrons, what have we done? We have done the excitation of electrons so that we get 3 unpaired electrons. With these 3 unpaired electrons, boron can form 3 sigma bond, one with the first fluorine atom and second and the third fluorine atom, 3 single bond, sigma bond. Okay, so here let's check out between which are orbitals the bonding has taken place. Okay, so over here let's check out. So boron has now 3 unpaired electrons. There is unpaired electron in 3s. There is unpaired electron in 2px. There is unpaired electron in 2py. Right? So let's not take the number, just the the orbital I'll just take. So this is for boron. And in fluorine, which are orbitals are unpaired? Let's check out. It is 2pz or 2p orbital of fluorine. How many fluorine atoms are there? 3 of them. So we have p orbital of the first fluorine atom, p orbital of the second fluorine atom, p orbital of the third fluorine atom. Now the orientation should be same. So whichever p orbitals are overlapping should be of the same orientation. So px will overlap with px, py will, if we are taking py will overlap with py of fluorine. Because as I already told you, if we take suppose this is pz, and suppose if this is pz, if this is px, I'm just saying if we can consider any of the p orbitals along any axis. So suppose if we consider that this is pz and this is px, the orientations are different, or the overlapping will not take place. Overlapping must take place if they have the same orientation. Like if we think that this is px, it will overlap with px. If this is py, it will overlap with py. So you can take any p orbitals along any axis. Okay. So there are 3 kinds of sigma bond: sp sigma bond, px sigma bond, py sigma bond. Okay. You can also take as instead of px, you can also consider along z axis, pz sigma bond. Okay. So these are the 3 types of, or the 3 sigma bond that is formed where in boron fluoride. Okay. I hope this is clear. Let's take another example with example 2 for water. Okay. So for water, hydrogen, there are 2 of them, 1s1, 1s1. Oxygen is 1s2, 2s2, 2p4. Okay. Now we have hydrogen, 1s orbital, 1s. For oxygen, 1s2, 2s2. This is 2p. So 1, 2, 3, 4. So spins I can draw anyway, but when we are drawing the electrons while overlapping, you can just show the opposite spin. Okay. So for now, I have the 2p. You can consider the p orbitals, two p orbitals of oxygen. They are half filled. They can overlap with 1s orbital of hydrogen, right? So suppose I take this as pz, and suppose I consider this as py. Okay. So suppose this is pz, and suppose this is py. Okay. So they have unpaired electrons. So they will overlap with 1s orbital of hydrogen. So this is the s orbital of hydrogen. Here, this will overlap with, py will overlap with 1s orbital of hydrogen. Okay. To give what? 2s, 2p, sigma bond. How many are there? 2 of them. Okay, so this is the Lewis structure for two sigma bonds. OH, single sigma bond. Well, you don't have to mention single because sigma means it is single bond. Okay, so this is the sigma bond or single bond. Similarly, you can practice for NH3. Okay, so NH3, 3 single bonds will be there, 3 sigma bonds will be there. Okay, so you can practice this ammonia. So I hope this is clear, the head-on overlap. Okay, it's not sidewise, it's head-on. Head-on. Okay, where the orbitals must have proper orientations. Okay, so if they have proper orientation, if the electrons are have opposite spin, half-filled orbitals, they overlap head-on to give you sigma bond or single bond. Okay. Now the second type of overlapping is the sideways, parallel, or lateral, or parallel overlapping. Okay. In this case, if the orbitals, they come near each other if the orientation is sideways, and if the orbitals come near to each other, here also the conditions are same. The electrons must have opposite spin, they must be half filled, the sign must be same. Okay, then they overlap in sidewise manner. To give you p pi bond. Okay, and also always in any molecule, first sigma bond is formed and then only pi bond is formed. When we practice one molecule, we will come across this information. Okay, always in a molecule, first which type of bond is formed? Sigma bond, then only pi bond is formed. Okay, and another information is that always for sigma bond, more overlapping happens, more overlap takes place for sigma bond than pi bond. So if the overlapping is more, what about the bond energy? Be stands for bond energy. If more overlapping, bond energy is more for which type of bond? Sigma bond. So bond energy more, where? In sigma bond. Yes? So bond energy is more in sigma bond compared to pi bond. Strong bond. Here, sigma bonds are very strong bond. So what can we talk about the bond length? Bond energy is more. Obviously, the bond energy is less, inverse proportion. So bond length is less. Okay, so this information is very, very important. Okay, now let's consider an example of oxygen, O2. Okay, oxygen, oxygen. 1s2, 2s2, 2p, 4. 1s2, 2s2, 2p, 4. So here I'm just drawing the 2p orbital. So 1, 2, 3, 4. This is 2p orbital. This is also 2p. 1, 2, 3, 4. Okay. Now, first, here we have Py is singly filled. Pz is also singly filled. Here also Py is singly filled. Pz is singly filled. Px is full, right? So in this case, suppose, so as I said, all the 3p orbitals have the same energy. You can consider whichever p orbital along whichever axis. Okay. So over here, suppose I'll consider this as pz. Okay. So the two pz orbitals of the two oxygen atom, they overlap head on. So this is pz. This is PZ. They overlap head-on to give you a sigma bond. Okay, so that's why I said first which bond is formed? Sigma bond is formed. Then after that, the py orbitals overlap sidewise. It's not possible to bring it more closer than this, so we denote it this way. This is py. So the py orbitals overlap sidewise to give you what? Pi bond. So there is a double bond between two oxygens. One is a sigma bond, the next one is a pi bond. First, which bond is formed? Sigma, and then pi bond is. Okay. So the electrons of the pi bond is above and below the nuclear axis. So this is the nuclear axis. So the electrons of the pi bond are above and below the nuclear axis. Okay. So because electrons are wave, they can be either above or below the nuclear axis. Okay. So this is how we represent the pi bond. Okay. The sidewise overlap. Right. So first always sigma bond is formed, then the pi bond is formed. Let's consider another example for nitrogen. Okay. So nitrogen and nitrogen. There are 3 bonds in nitrogen, just for the information. One is a sigma bond, and only one sigma bond is formed between 2 atoms. Okay, only one sigma bond can be formed. The next bonding will be pi, and if there is one more, it will be pi. Okay, so here, nitrogen, I'll just show with a diagram. One nitrogen, the configuration is 1s2, 2s2, 2p3. 1s2, 2s2, 2p3. Okay, so all the 3 2p orbitals are singly filled here. 1, 2, 3. For this nitrogen, for the second nitrogen also. 1, 2, 3. So all the 3 orbitals are half filled. So overlapping cannot take place between px and py. This will not take place. Py, pz. No. Or px, pz. No. These kind of overlapping will not take place because they have no proper orientation. This will not take place because the orientation is not proper. So as I said, the overlapping will take place between either it should be px, py, px, px, py, py, or pz, pz. Then only the orientation, whether it is head-on or axial. Okay, then only the orientations are correct or proper for the overlapping to take place. Okay, so here we have all of them, px, py, pz. Here also px, py, and pz. Okay, so let's consider this as the px of pz as of one nitrogen with the pz of another nitrogen. You can consider this as px also, no problem. So the 2 electrons, they overlap. So we get a sigma bond here. Okay, so pz, pz, sigma bond. Then py. What do we do with py? Suppose this is py of one nitrogen, py of another nitrogen. So I have py, py. So they will overlap sidewise to give you what? Py, pi bond. So first sigma bond is formed. Then only pi bond is formed. Okay. Third one. So this is px, suppose. Py, pz. So pz and py have done the bonding. Now left is px. Suppose I have px. Let's take green color. So I have px, px. This is px, px. Pi bond between px and px, also pi bond. So nitrogen, nitrogen, 3 bonds are there. One is a sigma bond, is formed first, then the 2 pi bonds. Okay? So these are the 3 bonds of nitrogen. Okay, nitrogen molecules. So one is sigma bond and 2 pi bonds. So nitrogen molecule has a triple bond. Right. Now, one of the common question that is asked, or one question that is asked is, find the number of sigma and pi bond in the following. First one, water. Second one, ammonia. Okay, so for water, we know I'm just drawing the structure. So 2 single bonds means how many sigma bonds are there? 2 sigma bonds. So I have 2 sigma bonds. Ammonia is 3 NH bonds, single bonds. So how many bonds are there? 3 sigma bonds. Okay. So the numbers is asked, okay? So then I have ethyne, C2H2. This is ethyne. I also have sulfuric acid, which we drew in Lewis dot structure. Okay. So ethyne, if we have. So these organic molecules, don't get worried, because gradually as we move in grade 11 and grade 12, you will be knowing the structures of all the molecules. So it will be easy to find out. For now, just a method to find out, just to find out how many sigma bonds and pi bonds are there. Okay. So carbon, hydrogen, carbon and hydrogen. So 1, 2, 3, 4. Carbon 4 valency must be satisfied for carbon. 1, 2, 3, 4. 1, 2, 3, 4. So carbon. So between carbon and between carbon and hydrogen, sigma bonds, right? And between carbon and carbon, if there's a triple bond, we saw one will be a sigma bond, the other 2 will be what? Pi bonds. So I have 3 sigma bonds and how many pi bonds? 2 pi bonds. Okay. Sulfuric acid, we drew the structure while we were doing the Lewis dot structure. I have sulfur is the central atom, bonded to 4 oxygen atom. Okay. And H is bonded to 2 oxygen atoms. And I have double bond for the 2 sulfur oxygen bond, because sulfur must have a covalency of 6. So 1, 2, 3, 4, 5, 6 maximum covalency. Okay. If they are single bonds, it's a sigma bond. Here, if it's a double bond, one is a sigma bond, one is a pi bond. Double bond here, one is a sigma bond, one is a pi bond here. So I have 2, 3, 4, 5, 6. 6 sigma bonds, counting once again, 1, 2, 3, 4, 5, 6 sigma bonds. And how many pi bonds? 2 pi bonds. Okay, then the next one is ethene, C2H4. So as I said, structures and formulas, don't get worried. So as you are learning in grade 11 and 12, you will learn most of the organic compounds and their formulas, okay? So C2H4 and also acetic acid. You will be learning about the functional group acid. You will be learning all these formulas, okay? Acetic acid. So ethene, there will be a carbon-carbon double bond, and carbon is connected, each carbon is connected to 2 hydrogen atoms. So this is the formula for ethene, okay? So if there's a single bond, straight away sigma bonds. And if there's a double bond, one is a sigma bond, other one is a pi bond. So how many sigma bonds are there? 5 sigma bond, and how many pi bond? 1 pi bond. Okay, then for acetic acid, this is the carbon is connected to, this is the acid group. Okay, you will learn in grade 12 about the acid. Okay, acid, aldehyde, etc. So this is the acid. In acid, this is a structure COOH. Okay, and the carbon is connected to 3. This carbon is connected to the 3 hydrogen atoms. Okay, so if there's a single bond, sigma bond, all sigma bonds here. Double bond means one is a sigma and one is a pi bond. So how many sigma bonds are there? 1, 2, 3, 4, 5, 6, 7. 7 sigma and 1 pi bond. Okay. So this is the how you count the number of sigma and pi bonds. Okay. Then one more example is C2CN4. Okay, so don't, as I told you, don't get worried about the formula for the organic compounds. Okay, this is the cyanide group CN. You will be learning about this. Okay, here for now, I'm just drawing the structure carbon-carbon double bond here just to identify the sigma and pi bonds. That's it. Okay, so carbon is connected to how many CN group, cyanide group? 4 of them. So definitely 4 bonds will be there. Okay, so 2 of them connected to each of the carbon. So this is C triple bond N, C triple bond N. Same way this side also, carbon triple bond N, carbon triple bond N. So wherever there is single bond, sigma bond, here sigma, 1 pi. Here's there's a triple bond. So sigma and 2 pi bonds. Sigma, 2 pi bonds. Here there's a sigma and pi bond. Sigma and pi. Okay, here just to identify or to count the number of sigma and pi bonds. Here 1, 2, 3, 4, 5, 6, 7, 8, 9 sigma bonds. 1, 2, 3, 4, 5, 6, 7, 8, 9 pi bonds. Okay, so don't get worried about the structure. Okay, so as you gradually learn with different organic compounds, you will be learning all the formulas. Okay. Similarly, there can be a question. Benzene. This is a structure. Benzene also you will be learning about the structure. This is a structure for benzene. Okay. How many sigma and pi bonds are there? So all the single bonds, let's write down. Then if there's a double bond, sigma and pi, sigma and pi, sigma and pi. So 1, 2, 3, 4, 5, 6 sigma bonds and 3 pi bonds. Then there can be a question. They might give you some molecules and they can ask you which of the following has same number of sigma and pi bonds. That's also an important and interesting question. Okay, so you must remember that if it's a single bond, it's a sigma bond. If it's a double bond, it's sigma and pi. If there's a triple, there's a single bond, it's sigma. If there's a double, one is a sigma and the other one is a pi. If there's a triple bond, one is sigma that is formed first and then the pi bonds. Okay, and the structures, as you go with different lessons, you will be learning more and more the different structures. So if you know the structure, you will know the number of sigma and pi bonds. Okay, now coming to difference between sigma and pi bond. And between them, which of them is stronger? Sigma bond is stronger than pi bonds. Okay, so if it is stronger, the bond strength is more. If the bond strength is more, the bond length is lesser. Okay, so sigma bond and pi bond. The first difference is that sigma bond is formed how? By axial or head-on overlap. Pi bond is formed by sidewise or parallel or lateral overlap. We saw both the examples, head-on and, sorry, I wanted to move up. Okay, second difference. Sigma can be formed between S and S. We saw this example for hydrogen. It can be formed between S and P. We took the example of HF, HBr, etc. Between PP also. But the orientation should be like PX, PX, PY, PY, PZ, PZ, like that. Okay. Sidewise overlap can be between PP. Okay, this also PX, then PX, like that. Orientation should be the orientation should be correct. Okay. Then we didn't study about P and D. We will be learning about it. And also between D and D, we will be learning in the next video. Okay. Third one is extent of overlap is more. Extent of overlap is more. So bond energy is more. What about if the bond energy is more? Bond length is less. Okay, and it's a stable bond, very stable bond. Strong bond. Very strong bond. Here the extent of overlapping is less. So the bond energy will be less. What about the bond length? Bond length is more. Because bond energy is inversely proportional to bond length. This information was given before. Okay. Now, sigma bond. In all these bonds we saw, even if it was multiple bond, double and triple bond, we have only one sigma bond is formed, can be formed. For pi bond, how many pi bonds can be formed max? One or two pi bonds. One or two pi bonds can be formed. For example, if I have a triple bond, one is a sigma bond, only one sigma bond is formed. The rest of them are pi bonds, right? So only one sigma bond can be formed. The rest of it is the pi bonds. Okay. And very important, and the next one, which is very important, is sigma bond can be formed alone. We saw the case of hydrogen, HF, hydrogen fluoride, like HH, HCl. It can be formed alone. It is not necessary that pi bond has to be formed. But in case of pi bond is formed with sigma bond. Okay, for example, oxygen. First sigma bond is formed, then pi bond is formed. So It cannot be formed alone. And in sigma bond, the rotation about the sigma bond is possible. So this is a sigma bond. The rotation about the sigma bond is possible. Okay. But in case of pi bond, the rotation is restricted. So rotation about the pi bond is restricted. It's not possible. It is very difficult. Okay. So these were the differences between sigma and pi bond. So students, we understood what is a sigma bond, what is a pi bond. We understood the differences between them. Okay, we practiced some molecules. Okay, we practiced drawing some overlapping of some overlapping of orbitals of some molecules. Okay, now we will be learning about d pi overlapping in the next video. Okay, students, that's all for today. Have a great day.